be joining?
So IT life. Please continue.
Okay. So hello everyone. Today we'll be discussing few of the questions that we saw for GATE 2025. I hope you've all done it very well. So let's just go over the questions from flight mechanics syllabus. Okay, so this was the breakup of the questions that we saw in the 2025 GATE. So we had 4 questions which were 1 mark each, and there were 5 questions which were 2 marks each, leading up to a total of 14 marks from flight mechanics section. So let's start with the questions. The first question that we saw was this. It says, a general aviation airplane is in steady and level flight. The airplane is prone to adverse yaw. Which of the following options best describes the deflections of aileron and rudder to achieve a coordinated right turn? So for a coordinated right turn, let's just draw this. Yeah, so let's just take this slide and we'll draw the aircraft. So if this is, just a minute. Yes, okay. So if we have, if this is your aircraft and assume these to be your wings, if we needed to turn right, coordinated right turn needs a roll towards the right and also a yaw towards the right. So in the question, it was mentioned that this aircraft is prone to adverse yaw. What was adverse yaw? When we want to roll the aircraft towards the right, and because of these rolling conditions, it yaws to the left. This is adverse yaw. How do we avoid this? We use our ailerons and rudder. Both the control surfaces are deflected in order to achieve this coordinated turn and to avoid the adverse yaw. So now let's see what we have to deflect to turn towards the right. So now if you have to roll towards the right, the lift on your left wing must increase and the lift on your right wing must decrease. Then we get this right roll motion. Okay, so how do you increase the lift on your left wing and decrease it on your right wing? How do you do it? You deflect your right aileron down. So if you deflect your right aileron down, delta A down, your lift increases. Here, similarly, you will have delta A up. Okay, so this gives you a right roll. Right roll. Now, if you also have to yaw towards the right, which direction would you deflect your rudder? If you deflect your rudder, if this is your rudder, and if I deflect it towards my right, there is a force generated in this way, right? So this is your minus Fy force, which leads to a positive yawing moment or yaw towards the right. So this is positive delta R or deflection of rudder towards the right. So for a coordinated right turn, you need to deflect your right aileron down, left aileron up, and rudder towards the right. Okay, so the right option would be option B. Left aileron down, the lift decreases. Right aileron up, right? So lift decreases proportionally to turn to roll towards the right. And this rudder towards the right creates your yaw towards the right. This is for roll and this is for yaw. Okay. So now let's go to the next question that we've come across in flight mechanics. So, for a general aviation aircraft, which of the following has a destabilizing effect on its static roll stability? Roll again was in the longitudinal axis. Okay, so we know that the dihedral angle does not, dihedral or the sweep back does not contribute towards roll stability. What is the confusing parameter here? It's the high wing or the low wing configuration. So, which of these contributes towards stability, which contributes towards destability? So, we had discussed this when we had gone over the questions. We had discussed this enough number of times. So let's just go over it one more time. So let's take a high wing configuration first. Okay. So let's take a high wing and presume it is subjected to a perturbation or some disturbance. What happens? It has a perturbation and it rolls in this manner. So now if it is a stable aircraft, it should return. Restoring moment should be there. What is the stabilizing moment? in this direction, right? To counter the disturbance. That should be your restoring moment. Then we can say the aircraft is stable. So for a high wing configuration, there is a component of oncoming velocity that hits in this manner, which produces this restoring moment. So high wing configuration is stabilizing in terms of roll. Now let's look what happens for a low wing configuration. So same thing, low wing configuration subjected to the same disturbance. It looks like this. Now the same component of oncoming velocity for a low wing configuration, you can even think about this intuitively. The low wing configuration has a component that acts in this manner. What happens now is that the moment produced due to this thing further destabilizes your aircraft, further moves in the direction of disturbance. So there is no restoring component. So look at the question carefully. Which of the following has a destabilizing effect on static roll stability? So we know that low wing has a destabilizing component associated with roll stability. Okay. All right. Go to the next question. A general aviation airplane is flying at an altitude of 5,000 meter. The indicated airspeed is 250 km per hour. Assume that there are no instrument errors and no position errors, and assume that we are neglecting the compressibility effects. Which of the following options is false? So before we go into the options, let's just discuss the different types of airspeed. Okay, so what is given in the question is your indicated airspeed. What is indicated airspeed? The one that's indicated on the instrument. So this is given to you as 250 kilometers per hour. 250 kilometers per hour, whatever is indicated in your device, right? Next is the calibrated airspeed. Calibrated airspeed. What is calibrated airspeed? It is this IAS, which is indicated airspeed, which is corrected for instrument and position errors. Okay, so it is the same IAS which is corrected for instrument and position errors. But since the question clearly mentions that is no instrument error and no position error, in our case, in this question, the calibrated airspeed and indicated airspeed will be the same. So we'll take it as 250 kilometer per hour just for this question. Okay, next thing is true airspeed. Before that we have one EAS, equivalent airspeed. So this is when is the CAS is accounting for the compressibility effects. Again, in our question, it says that there is no compressibility effect, neglecting the compressibility effect. So our EAS will also be same as CAS, which again is 250 kilometers per hour. Again, just for this question. Okay. Then we have the true airspeed. What is true airspeed? True airspeed is the actual airspeed which accounts for the density effects. Now, because accounts for density and altitude, right? So because this aircraft is flying at a higher altitude, its density at that point will always be lesser than the sea level density, right? And because of that, your true airspeed will always be higher than indicated airspeed. So the formula we know is uh, how these two relate is true airspeed is indicated airspeed into under root of rho naught by rho, where rho naught is the density at sea level, rho is the density at which the aircraft is flying, right? This rho is less than rho naught, and hence TAS is always greater than IAS. Okay, so TAS always greater than IAS. Now look at the questions, and they've asked you which of the following options is false. Okay, true airspeed is greater than 250. This is a true option. Calibrated airspeed is 250. Again, true. True airspeed is 250. This is wrong because we know that the true airspeed will always be higher. So they've asked you which is false, and hence C is the correct answer. Okay, let's go to the next question. Okay. To achieve longitudinal static stability of a general aviation airplane, which of the following conditions should be satisfied? Longitudinal stability, this was a fairly simple question, straightforward. Let's go over the points that we discussed in general for longitudinal stability. Okay, so point number one, I hope you remember the graph, which is Cm versus alpha. Cm is pitching moment coefficient, alpha is angle of attack. For a statically stable aircraft in the longitudinal sense, this graph will have a negative slope. Okay, what does this mean? Your Cm alpha or dCm upon d alpha is less than 0 for a stable aircraft. Okay, so let's look at the options, which is this. Yes, the point number C shows that Cm alpha should be, oh sorry, that is the, yeah, it should be positive, it should be negative, that should be our point, right? Which of the following conditions should be satisfied? So C is wrong. Your Cm alpha should always be negative. This was the first and foremost condition that we had seen, correct? Next, what do we need? If you take the aircraft fuselage reference line, if this is your neutral point for a stable aircraft, where should the CG be? CG should be ahead of the neutral point. Why? Right? CG should be ahead of the neutral point. Why? Because if it is subject to a gust, you are imagining your aerodynamic forces to be acting at neutral point, right? We have transferred the forces from center of pressure to neutral point. Now, if there is a gust or some disturbance and it's deflected from its equilibrium position, only if your neutral point is behind CG will there be a restoring moment. Okay, so this is one condition. This is condition number 2. And then we had seen something known as static margin, right? What was static margin? Static margin is x bar np minus x bar cg. Now, if your cg is ahead of neutral point and you take some reference point here, your x bar np will always be greater than x bar cg for a stable aircraft. So, static margin also will be greater than 0. This is point number 3. Correct? So now let's look at the options. Center of gravity of an airplane should be aft of neutral point. No, this is not true. Center of gravity of an airplane should be forward of the neutral point. Yes, this is correct. Next option. The stability coefficient dCm upon d alpha is positive. No, it's not true. It should be negative. Static margin is negative. Again, untrue. Static margin for a stable aircraft is positive. So the only correct option is B. Okay, let's go to the next question. Okay. A general aviation airplane is initially in a steady and level flight. The stability coefficient dCm upon dq, okay, q is the pitch rate here. dCm upon dq is negative. The airplane is perturbed with a small nose-up constant pitch rate. Assume that the horizontal tail does not stall during perturbation and unsteady effects are neglected. When compared to steady and level flight condition, which of the following statements is or are true during the perturbed motion? So please read the question very carefully. They've given some conditions which may lead to confusion. Okay, so one thing that you need to remember is horizontal tail does not stall during perturbation, unsteady effects are neglected, and this coefficient is negative. So like we've seen in the previous case, if dCm upon dq is negative, the aircraft is longitudinally stable. Okay, now let's look at the conditions. Okay, the angle of attack of the horizontal tail increases. Now remember that in the question they said it is subjected to a nose-up perturbation. So if your aircraft was initially like this, where you have the wing here and you have the tail here, it is subjected to a nose-up perturbation. What happens? The fuselage reference line is inclined, your wing is here, and your tail is here. This was the original line, right? So when it is subjected to a nose-up perturbation, the angle of attack at the horizontal tail increases, as is evident from our figure. So what was the question? Which of the following are true? So angle of attack at horizontal tail increases is true. Correct? Next, the contribution of horizontal tail to the airplane's pitching moment about center of gravity is more stabilizing. Now let's look at this. So now when the angle of attack at tail increases, when alpha tail increases, right? When alpha tail increases, what happens? The lift at the tail increases. So this leads to a lift at tail increasing. So that means there is an increase in lift here. So delta L. There is an increase in lift due to increase in angle of attack. What does this do? This creates a nose down moment about CG, which is somewhere here. Okay, nose down moment. So it is producing a restoring moment as opposed to the disturbance. So the contribution of horizontal tail towards pitching moment is stabilizing. Now we need to remember here that this lift will increase until stall is what we have learned. But since we are neglecting the stall effects, there is no such limitation on our assumption. Okay, next, the lift generated by the horizontal tail increases. Yes, because angle of attack increases, lift generated increases. Again, there is no stall, so it increases. You can just, this is a correct statement. Right. Then the contribution of horizontal tail towards airplane pitching moment about center of gravity is less stabilizing. That's not true. We just saw it produces a restoring moment. So the correct options are A, B, and C. Okay. Next. Yes. A general aviation airplane is gliding with a speed Vg at minimum glide angle. Okay. The minimum glide angle is Vg. Which of the following statements are true? Now, let me just take a fresh sheet. Okay. So, what was your glide angle formula? Theta g was tan inverse of 1 by L by D. This was the formula that we're working with. Now, if I say minimum glide angle, when does this occur? At L by D max. So, theta g minimum will occur at tan inverse 1 by L by D max. Correct? Okay, so this is the first point that we have to see. Let's look at the first option. Vg is equal to speed corresponding to maximum lift drag ratio of the airplane. So this is true? Correct. Then Vg increases with decreasing wing loading when all other parameters remain constant. What was the formula for any velocity? So let's just take V is equal to under root 2W by rho S CL. Similar formula can apply to Vg also, right? So it is directly proportional to the under root of wing loading. Wing loading is W upon S. So this statement is false, right? Because if wing loading increases, Vg also will increase. It's directly proportional to the under root. So this statement is false. Next, Vg increases with decreasing altitude when all other parameters remain constant. Again, let's look at the same formula. Okay, so if your altitude is increasing with increase in h, density reduces. Correct? So, which of those two statements will be true, C or D? First is Vg increases with decreasing altitude. Next is Vg increases with increasing altitude. With increasing altitude, your density reduces and Vg increases, right? So point number D, this is true. Okay, now let's go to the next question. In a low-speed airplane, a venturi meter with 1.3:1 area ratio is used for airspeed measurement. The airplane's maximum speed at sea level is 90 meters per second. If the density of air at sea level is 1.225 kg per meter cube, the maximum pressure difference between inlet and throat of venturi meter is in kilopascal, rounded to 2 decimal places. Sorry. So let's try solving this. Okay, so they've given you area ratio. So A1 upon A2 is 1.3. Correct? 1.3. Now the maximum speed at sea level is 90. So if I take V1 is equal to 90 meters per second. Correct? Now let's use the continuity equation. It is A1 V1 equals A2 V2. Now upon substituting all of these formula, what do we get? We get V2 is equal to A1 by A2 A1 by A2 into V1. When you substitute everything, you get 117 meters per second. Now we use the Bernoulli's equation, which is P1. So this was the first equation that we used. This is the second one. P1 plus half rho v1 squared equals p2 plus half rho v2 squared. So I'll just take another sheet. We'll continue this. So write it in terms of the pressure difference because the question asks for the pressure difference. I'll just rewrite the equation. P1 plus half rho v1 squared equals P2 plus half rho v2 squared. Now we'll rewrite the equation in terms of pressure difference. Okay. So delta P equals P1 minus P2 equals half rho v2 squared minus v1 squared. Okay. Now let's substitute the terms. We get half into 1.225. This was given in the question directly. V2 we have found out 117 squared minus V1 is given in the question 90 squared. Now upon substituting all of this we get 3422.21 Pascal. In the question they've asked you kilopascal rounded off to 2 decimal places. So you get 34.22 kilopascal. Oh, sorry, 3.42. Sorry. It's rounded off to kilopascal. 3.42 kilopascal. So this is the right answer. Okay, now let's go to the next question. Okay, a jet-powered airplane is steadily climbing at a rate of 10 meters per second. The air density is 0.8 kg per meter cube. The thrust force is aligned with the flight path. Thrust force is aligned with the flight path. Using the information provided in the table below, the airplane's thrust to weight ratio rounded off to 1 decimal place is. So they're giving you airplane speed, lift coefficient, aspect ratio, Oswald's efficiency factor, zero lift drag coefficient. Okay, now let's take a sheet and start trying to solve this. Okay, so what is given to you? Let's write down whatever the data is given to us. Climb rate is 10 meters per second. Density is 0.8. Then you have velocity is 80 meters per second. Then we have CL is 0.8. Aspect ratio is 6. Oswald's efficiency factor is 0.8. Your CD naught, that is zero lift drag coefficient, is 0.02. Now they've asked you for thrust to weight ratio. So what was the thrust formula? Your thrust is D plus W sine gamma, right? So now sine gamma we know is Vc upon V, right? Vc is the climb rate, V is the oncoming velocity. So we get this directly as 10 by 80 is 0.125. Now we got sine gamma. We need the thrust to weight ratio. So we can divide the entire equation by W. But before that, we'll need to find out drag, right? So thrust to weight ratio is drag upon weight plus sine gamma. Sine gamma we have already found out. Now how do we find out drag? So let's come back to this equation. We'll find out drag in first. Drag is half rho v squared s CD. Now we need to find out CD. We only have CD at zero lift drag. So find out CD. CD is CD naught plus KCL square. CD naught is 0.02. Oh, I missed this 2 here, 0.02. So it's 0.02 plus KCL square. What was K? 1 by pi E AR and CL. CL is given to us as 0.8 squared. Now upon substituting everything, what do we get? We get this as 0.0624. Now plug it into this drag equation. CD is this, alright? So plug it into the drag equation. We get half rho V squared S CD. Now, before that, we also don't have the other parameters, right? We don't have S, half rho V square and all of that. So what do? It's given as a steady level flight. So you can assume that. So you have lift equals weight. So this was one assumption. This is another. Lift equals weight. Okay. So from there you get half rho V squared S CL. Now from here you get the equation of S and you can plug it in here. So you get half rho V squared, and in place of S you take it from this equation. Alright. So you get 2W by rho V squared CL, and this is CD. Okay. So let me just erase a few things. So I'll just, okay, let me just remove this. We'll write it down again. Yeah, okay. So I'll just write that sine gamma here is VC by V is, what was the value that we got for sine gamma? Just a second, yeah, it was 0.125. Okay, so now let's continue this drag estimation. So when you cut off all of those terms, what you finally get is W into CD by CL, which is nothing but 0.078 W. Now let's go back to our main equation, plug it in here. So if you do drag upon weight, you get 0.078 plus sine gamma is 0.125. So you get final value as 0.203, and they've asked you to round it off to one decimal. So you get 0.2, right? So this is your final answer. So we start with this equation. Then we find out drag. To find out drag, we need your CD naught, CD equation. For that, we find out CD naught plus KCL square, substitute it into the drag equation, and then plug it in here. Okay, just proceed step by step, and then you'll see that some terms cancel out. All right. Okay, now let's go to the next question. Okay, while taking off, the net external force acting on an airplane during the ground roll segment can be assumed to be constant. What does this mean? If the net force is constant, the acceleration is uniform, is constant, right? Right, Newton's laws of motion. So if the net force is assumed to be constant, the acceleration is constant. Okay. The airplane starts from rest, so initial velocity is 0. SLO, VLO are the ground roll distance and lift-off speed respectively. Now they've given you alpha VL naught, where alpha is greater than 0, denotes the airplane speed at 0.5 SL naught. So at half the ground roll distance, what is the speed? Alpha VL naught. Okay. Neglecting changes in the airplane mass during ground roll segment, what is the value of alpha? How do we proceed with this? You can either use your work equation. What is the work equation? W, work done, is equal to change in kinetic energy, right? Delta kinetic energy. So what does that lead to? Force into displacement. That is the work done. Force into displacement is change in kinetic energy. That is half, and they've told you to assume mass remains constant. So half mv squared minus half mu squared. This is one way you can do this using this formula, or you can use your basic kinematics equation. Okay, so what is the kinematic equation? This is the second way. You can, using both ways, it follows similar steps almost. So let's just try doing it using kinematic equation. So v squared equals u squared plus 2as. This was the kinematic equation. Now it starts from rest, so u is 0. So now at 2 points for the entire takeoff distance and for half the takeoff distance. Okay. So for A, that is the entire takeoff distance, what is the formula? VL naught squared. U is 0. Okay. So U is, it starts from rest, so U is 0 equals 2A SL naught. Then second case for half the ground roll distance. What is the formula? Just plug it in over there. So alpha VL naught whole squared equals 2A and 0.5 SL naught. Right? So now if you divide equation A by equation B, what do you get? Or just do it the other way around, because you need to find out alpha. So you have alpha squared VL naught squared by VL naught squared equals 2A 0.5 SL naught by 2A SL naught. Now all of the common terms you can cut out and you get alpha squared equals 0.5, right? Where alpha is equal to 0.707 and they've asked you to round it off to 2 decimal places. So it is 0.71. Yeah, so this is the right answer. So if you follow the work done formula also, you will follow almost similar steps. You will have the same U is again 0. Do it again for the complete ground roll distance and for half ground roll distance, and you will get the same formula, same answer. Alpha squared is 0.5. Square root of that is the final answer. So I think this was the last question from the flight mechanics segment. I hope this was clear to everyone. It was fairly simple, straightforward questions, except there were some terms, some sentences given in the question that may lead to some confusion. But if you read it carefully, I think you should have been able to solve it. So I hope you were able to do it. I hope this was clear. So I think we'll end the session here. Yeah. So, thank you.
Yeah, thank you. Please move to
Thank you.
our questions, Tanya. I think some MSQs were tricky, right?